Hi everyone, my name is Xin Chen. Today I'm presenting our paper, Better Zero-Shot Reasoning with Self-Adaptive Prompting. So recent progress has enabled large language models, or LLMs, to perform well on reasoning tasks, even though they historically struggle on those tasks. And one of the technique monumental to that is chain of thought, or COT prompting. And few-shot chain of thought, as shown on the illustration on the right, use handcrafted step-by-step solution to similar problems as in-context examples. On the other hand, zero-shot chain of thought is more general. It directly prompts language model to generate reasoning spontaneously with triggers like let's think step by step. However, there is still a gap between few-shot and zero-shot chain of thought because on the zero-shot, language models are not shown with a template rationale and can often output spurious logic. But large language models are general purpose and typically used in a wide range of tasks. So it is troublesome to handcraft few short demos for a lot of tasks. So the question is, can we use in-context learning even in zero-shot setup using the large language model's own output? But there are several challenges, such as sensitivity to prompt choices, and the own outputs can be wrong and misleading. And how do we choose large language models' own output without accessing any ground truth labels? So that's what our work is trying to do. We propose Cosp, and the TLDR is that with self-consistency and similarity as a quality metric, we use rationales generated of large language models themselves as in-context demo. And the advantages is zero-shot, black box, and inference only, and can thus be used in a wide range of different large language models. And now I'm going to talk a little bit on the actual methodology. And this figure gives an overview of the Cosp framework, divided into two stages. In stage one, we generate a pool of candidates, and we also design a score function to decide which model generator response we're going to use as in-context examples. And in second stage, we're actually going to prepend those queries to the test query, and then we're going to ask the language model again, but using a format similar to few-shot chain of thought. So now to the details. We begin by building a candidate pool. For each test query, we query the large language model with zero-shot chain of thought m times, and to extract m different reasoning paths and potentially different answers. And then we take the insight from self-consistency paper that majority predictions are more likely to be correct. We only retain the majority prediction of each test question in the pool. And then we follow that by scoring the different responses based on the belief that consistent or more confident predictions are more likely to be correct. And we quantify using this normalized entropy. To give an example, if the large language model generates m different answers for m different decoding, then you have a maximum entropy of 1. On the other hand, if for all the m decoding steps, it reaches the same answer at the end, then you will have entropy of 0. And we can see here that entropy is actually a good proxy of ground truth correctness, as correct and wrong answers end up having very different entropy profile. And we also introduce repetitive penalty because we observe that repetitive demos can lead to very bad model responses. So we use a simple metric to measure the repetition among each responses, and we penalize the large language model from choosing those as the in-context examples. And to get the overall objective function, we just add the term together. And when we choose multiple demos, we also introduce a green term, which is to induce diversity among the different demonstrations. And in second stage, we simply concatenate what we have obtained in stage one into the test query, and we query the large language model again. We take the majority vote as a final prediction. And now to the results, we have looked at different data sets, numerical and logical, and we also consider 3 different large language models. And we also compare against a few baselines, including zero-shot, few-shot, and also auto-COT, which is another previous work, also looking at zero-shot pseudo demonstration construction from the model's own generated output. And we can see that from the results, our Cosp greatly outperformed the zero-shot baselines. And in many cases, it's actually comparable, even better than the few-shot baselines, even though Cosp is zero-shot. And you can see the similar trend holds in GPT-3. And lastly, I'm going to give some example prompt of what Cosp has discovered on GPT-3. So this is a data set where GPT only has around 30% accuracy, but we can see that all 5 examples selected by Cosp are actually correct. So that shows the effectiveness of our scoring and selection procedure. And to summarize, we propose Cosp, a method aimed at improving zero-shot reasoning of large language models through their own output selected via consistency, repetition, and diversity. And for the future work, we're interested also in generalizing beyond reasoning tasks because we believe that the principles can be universal. And thank you very much for your time.